Hello, welcome to the Henstitute, the Hennon Institute of Physics. This is Mr. Hennon, and we are going to be doing our best to introduce the concepts in AP Physics 1. So we're going to jump right into Chapter 1, which is entitled Introduction to Mathematical Concepts. And one of the things that you're going to find out right away is I'm going to try to break this up into little sections. But if we get into this, we really need to answer this question: what in the world is physics? If we are going to be answering this question, someone asks you, what are you taking, what are you doing? You're going to say, okay, I'm studying physics. And they're going to say, what is it? We know it has the word physical in it, but what does that actually do for us is going to be important. So let's grab, if we do a quick internet search and see what they have to say about it. One of the things that you will find is this is what they will come up to describe what exactly physics is. So this is what we're going to kind of take a look at as our definition. So physics is a natural science studying matter. It's going to study motion. Those are key things. And it's behavior. It's related to different entities such as energy and force. Those are going to be big ones throughout the year. And really, one of the things I think is most important in this thing, in this description, is the word how. We are trying to understand how the universe behaves so we can predict other things that are going to happen. So the book goes through all this and talks about how both men and women have been doing this. We'll try to highlight some of that, all the different phenomena, whether we talk about planets or radio waves or magnetism, that type of stuff. We're going to deal more with the basics of it. And we'll definitely get into Newton's laws of motion. That's going to be a really big one. And when we do these experiments, we're trying to find things that we can be accurate and reproducible with. And if we're going to do that, we have to understand the concept of units. So that's the first thing we're going to get into, is describing units. Here in physics, we use what are known as SI units, which are the International System of Units. So for length, mass, and time, we're talking about the meter, the kilogram, and the second. Chemistry sometimes uses centimeters, grams, and seconds, but we're going to be dealing with meters and kilograms. And then here in the United States, we use the British Imperial System, which technically uses the foot for length. If you were going to get picky with mass, it should be the slug, but you'll probably also relate this to the pound when we get into forces and masses. We'll talk more about that. But they also still use the seconds, which is kind of nice. So we're going to have to do some of this converting into what we refer to as the base SI units. But we'll also have these derived units when we get into things like force and energy, like we mentioned earlier. We're going to see some of those. And one of the things that's really nice about the metric system is all these prefixes. These different prefixes can just slap right on the front of the word meter, and they represent different things. For example, if you say you have 1 nanometer, then you have 1/1,000,000,000 of a meter, which is 10 to the negative 9 meters. Most people are probably mostly familiar with the kilogram down here. Kilo means 1,000, so if you have a kilometer, you have 1,000 meters, or 10 to the third meters. If you have a kilo of anything, you actually have 1,000 of those things. So if you have a kilo dollar, you have $1,000. Some of us have a kilo dollar. We also want to be able to convert into our different units. So we've got meters and inches and that type of thing. So we'll look up all these conversion factors. If you were in class, I have a nice little conversion factor sheet that we use. I may post a PDF of that onto the Google Classroom, but with you online right now, you can probably look most of this up just as quickly. The book kind of goes through a setup for a reasoning strategy when you're trying to convert. I figure you're probably somewhat familiar with it, so let's jump into an example. Let's say that you had to try to figure out how high in feet the tallest waterfall is, which is Angel Falls in Venezuela, which has a total drop of 979.0 meters. Well, if we were going to convert this into feet, what would this be? The first thing I would always highlight if you're going to do any kind of converting is write out your initial measurement. So we write 979.0 meters. Then you're multiplying by some kind of conversion factor. You're going to take whatever unit you're trying to get rid of, you're going to put it on the bottom down here. We're going to put our meters down here. And ideally you want to put whatever you're trying to convert into on top, into the numerator. Now if you can't do that, at least go to another unit that you can potentially convert from there, and you should be good. If I go back a few slides, I saw there was a conversion. 1 meter is equal to 3.281 feet. So that's one possibility. However, you'll also notice here that 1 foot is 0.3048 meters. It doesn't actually matter as long as you are matching the number with the unit. So you're matching the number with the unit, you should be good. I'm going to use this top one. I'm going to use the 3.281. So there are 3.281 feet in 1 meter. 5 by meters. Since I'm dividing by 1, I really just have to take the numerators and multiply them to get my answer. Pull out my handy dandy calculator here. Let's see what we can get. So 979.0 multiplied by 3.281. And we get 3212.099 feet. Now, one of the things we're going to get into is also the concept of significant figures. Significant figures is a place that I want you to start rounding things off. In other words, when you are actually giving me a final answer, I don't want you to give me the full calculator answer. This answer up here has all of the different numbers the calculator is giving me, but I probably don't know it to the nearest thousandth of a foot when I'm actually trying to find this. So I need to round it off a little bit. Your original number is going to help us with that, and actually the numbers in the problem always help with that. So, a couple of rules. First rule for significant figures. If it's a non-zero, it's counted. So right now I have 979, that's 3 of them. So I definitely have 3 significant figures. The other rules all deal with zeros. If you have a zero between non-zeros, it would get counted. So if this was 909, 0.0 meters, then I still have 1, 2, 3 there, and those would get counted. The next rule that deals with zeros is the ones that don't get counted. If you have a zero that is to the right of a decimal point, but to the left of a non-zero number, or vice versa, to the left of a decimal point and to the right of a non-zero number. In other words, if it's between a decimal point and a non-zero number, it does not get counted. So if this was just 900 meters, actually I'm not going to do that, if I just had 900 meters, then the understood decimal place here would be right there, and this would just be 1. These zeros would not get counted, really because you can convert this into scientific notation and write it as 9 times 10 to the second meters. And those zeros disappear, and this is the only number you would need to write. So that's one of the rules. If this was 0.009 meters, same situation. This would only have 1. These would not count because they are between a decimal and a non-zero number. Basically the same idea. You can write this as 9 times 10 to the negative 3 meters, and you can get rid of them. However, with that in mind, this zero over here is probably the strangest one. If you have a zero that's to the right of a non-zero and to the right of a decimal place, it does get counted. So this one actually would get counted. This actually has not 3, but 4 significant figures because this one does get counted. And the same thing would happen here. If I suddenly made this 900.0, that's why I got rid of it, it would actually make the other zeros become significant. It's kind of weird. So try not to have that happen very often, but it occasionally happens. So really I've got 1, 2, 3, 4 of them. These don't actually get counted in terms of significance. Basically what that means is my precision. I can only tell you that the height of the falls is 3,212 feet. That's as precise as I can get to the nearest foot. I can't go to the nearest thousandth of a foot. And it has nothing really to do with the original numbers up here, and we'll see more of this as we implement some other examples. Let's try another one. What if we're doing speeds? What if we're trying to convert some speeds here? So with speed, we have a couple of ideas. One, I would still write this So 65 miles per hour. What I want you to get in the habit is don't do things like this. Don't write MPH. I don't like that because M to me is always going to be meters. So I don't want you to write that. I also don't want you to write miles per hour like this. There was this slash like that. It's going to throw things off. And so instead, if you were to write miles per hour, your best bet is to actually write miles divided by hours. Or in other words, 65 miles per hour means 65 miles per 1 hour. That way, when you're converting this, you can see your miles are going to go in the denominator. You're trying to convert this into meters, so you're going to put meters up top. You're looking for a conversion factor that does that. If you go back a few slides, you'll find out that 1 mile is 1,609 meters. We'll go back a few slides to see that. So 1 mile is 1,609 meters. I think that's the easiest to actually do a conversion, rather than trying to do something else. You could try to go to kilometers and then convert over. That would work, but that's just going to be longer than you need. That's going to get rid of your miles. And then we do the same thing with our hours, but this is why I wrote it that way. So I want you to realize that now hours is going to be on the top, and seconds is actually going to be on the bottom. It's going to be in the denominator. And so here I'm trying to find a conversion. We know that there are 60 seconds in a minute and 60 minutes in an hour. I take 60 times 60. That's 3,600 seconds in 1 hour. That's going to get rid of my hours and leave me the seconds. Now I've got my meters per second. We just have to convert this over and we should be good. Pull out a digit calculator. I think 65. I'm going to multiply just by 1609. So there's a number on top. I'm going to end up dividing by 3,600. And I get this 29.0515. Well, but we don't get to keep all those. We just get to keep the 29 meters. Now you can also do a conversion like you were talking about before, is some people like to write miles per hour like this. If you're going to do that conversion, you've got to keep that miles per hour together like it's one solid unit. And you would put meters per second like it's one solid unit as well. And you would need to look up some kind of conversion factor between these. The one that I tend to use is 1 mile per hour is 0.447 meters per second. You look this up. So this would be 0.447 means 1 mile per hour. Now the entire miles per hour is canceled, and you're left with meters per second. And guess what? You also get 29 meters per second. So this is just kind of a review of some of the concepts dealing with converting units. I hope this helps, and you enjoy this first edition of the Institute.